Okay, so today we're going to take a look at the magnetic equivalent of Gauss's law. It's called Amperes Law. It functions in many ways like Gauss's law, except Gauss's law is for electric fields, and Amperes law is for magnetic fields. And it's not just a difference of saying, oh, it's a different type of field. Remember, electric fields and magnetic fields are different in a couple of different ways. Now, they're very similar in many ways, but one of the biggest things that makes them different is for electric fields, I can have a positive charge off by itself, and I can therefore have an electric field that points out in all directions. So what we would do is we would set up a Gaussian bubble, and however many lines would go through that Gaussian surface would be directly related to how much charge we had enclosed in it. Here's the problem. If we do a Gaussian surface, a Gaussian bubble, like we did before, so I want you to imagine that this is a spherical shell, a bubble around it. I want you to think about this. If we have a magnet instead, we've got a north pole and we've got a south pole. And one of the big differences about magnets is they always come in pairs, and more to the point, the magnetic fields are always closed loops. The magnetic field lines point the direction they north would go. They point from north over to south. So we end up with this. Here's the problem. If I take my Gaussian bubble, I'll draw it in blue in this case, or I'm sorry, in red. Let's go ahead with red. But if I were to take a Gaussian bubble like this, just like we did where it's a spherical shell, it's a bubble around our magnet, the problem is this. Since magnetic fields are always in closed loops, however much goes out comes back in. However much goes out comes back in. They have to, because all of the field lines continue to loop back around based on one of the fundamental things we've talked about in class. Magnetic fields always come in closed loops. That's what makes them noticeably different from electric fields, where we can have a net charge and the charge's electric field can kind of go off to infinity. We can have lines coming through the bubble. We can have a net flux. In this case, with our setup here, if we encase the entire magnet, then since the magnetic field lines are closed loops, whatever goes in goes out has to come back in, and our net flux for a magnetic field through a Gaussian bubble, a Gaussian surface, a closed surface, it will always come up to zero because we have just as much going out as coming back in, which means we are not going to be doing what Gauss's law has, which is the integral, closed integral of the electric field over a surface area, a bubble, an enclosed area. That was Gauss's law. That's Q enclosed divided by epsilon naught. What we're going to learn is Amperes law has to be adjusted slightly, and that's why it's not simply Gauss's law again for magnetism, because we have to use an entirely different surface. We're not going to use an enclosed bubble. We're actually going to use a closed loop. A good example of this, well, let me write this out. Amperes law is a closed integral of the magnetic field dotted with a length, not an area. We're not integrating over a bubble, an area enclosing space. We actually have a loop that encloses an area, and we are going to integrate around that loop. And it will be equal to mu naught, the permeability of free space, times the current enclosed. Amperes law looks at moving charges and uses them to actually generate the magnetic fields. Now, in many ways, it will act exactly like Gauss's law, and hopefully we've spent a good amount of time on Gauss's law, so this will be much easier for you to adapt to. That being said, the biggest difference is instead of by having an area, a bubble, we're going to instead have a loop, a ring, basically. Now, we can use a couple different geometries, but the main one that you're probably going to end up using, because we're usually looking at wires of one kind or another, since a current must go through it, you'll usually use a circular loop, basically a little ring that you put around it. All right. Let's go ahead and jump right into the problem. I'm going to take what is both a combination of a relatively simple one and combine it with a very difficult one. You're going to see that the math doesn't actually look all that great on the second part. However, here's what we're going to do. I'm going to bring in some technology. This is an old-fashioned cable. It's called a coax cable. It's the sort of thing that cable companies would use, that sort of thing. They're actually used all over the place. But it's coax for short. It's actually coaxial. And if we were to cut this open, which I'm not going to do because it's a perfectly good coax cable, but what you're going to find on the inside is it's got one wire that runs through the very center of it. But then what it also has is another wire that's basically a donut shape, like this, that runs along like this. In other words, we basically have one piece of metal that's in the middle and is just a regular wire. And then what we've done is we've taken, effectively, another piece of metal and we've wrapped it around as a little collar. And then we put something that doesn't conduct in between them so that when I put charges, current, through the one in the middle, it doesn't go over to the outside edge. In fact, what normally happens to complete the circuit is you'll have the incoming current come in through the middle, and then it'll go through your circuit, your cable box, for instance, or many other places that use coax cables. Some of our equipment here in the lab actually uses coax cables to transmit a signal. But then, as the current goes through that circuit, does what it needs to, it comes back out to complete the circuit. It will actually go back out the metal on the outside edge. In fact, that's how we're going to treat it today with our coaxial cable. In fact, that's where they get the name. You have basically one cylinder and a hollow cylindrical shell, effectively, around it, but they both share the same axis, so they are coaxial. That's where we get the name. All right, here's what we're going to do. We're going to say that we have, so from a side view, it looks like this. We've got a wire in the middle, and we've got a shell that goes around the outside edge. So we've got some metal here, and we've got some metal here. And usually they are separated by some material, a dielectric of some kind, so that charges can't go from this one over to there. They can only go through the wire itself. What we normally find is this, that the current is going one way in the middle and it's going the opposite way on the outside edge. It's basically a way to create a circuit with just the one wire. So we connect one wire from our source, the current comes in here, does what it needs to in the circuit, and then comes back out the other way to go back to the source, the battery, or the voltage supply. All right, here's what we're going to do. We're going to assume the following. I'm going to draw it from the edge on. So instead of having the wire sideways, which is what we did initially, I'm going to have it pointed right at you, and that's what we're going to solve with. So I apologize, the focus of the camera might be going in and out because it's trying to follow me, and I'm a little bit closer than usual. All right, here's what we're going to do. I'm going to draw this from the side. We've got a wire in the middle, and I'm going to say that it has a current, I, coming out of the board. As a reminder, dots imply, well, that's a notation that says that we've got something coming out of the board or out of the page towards you. We've got some empty space here, and then we go to the outer part out here, and I'm going to say that we have an equal but opposite current going into the board. So we have the current coming out, doing some stuff, and then going back in through here. And what we're going to say is this. I'm going to call this region 1, C. The inner wire, we're going to say, has a radius of r. The radius out to here, we're going to call 2r, and the radius out to the outer edge is going to be 3r. Now, in real life, I don't think those are the actual dimensions of a standard coaxial cable, but we're going to go ahead and do that. I'd rather do that than say R1, R2, and R3, which would be something that would solve for the real coaxial cable, mainly because I don't want to have a whole bunch of variables that we're dealing with, and I want to show you how you could work with this. On top of that, in Gauss's law, it was normal for us to deal with things that all have the same base value, R, and then we'd have 2 or 3 times on it. That being said, you can still do this full derivation with R1, R2, R3, however you want to go about this. Here's what we're going to do. I want to find the magnetic field around this wire as a function of some distance, little r. Now, I want to find the magnetic field at all points going from the very center of the wire all the way out to r equals infinity. So I want to go from little r is, 0 is less than or equal to little r is less than or equal to infinity. And I want to know what the magnetic field from this wire as a function of r will be. Here's where we're going to start applying it. Now, the first thing that I will say is this. It is both an easy sample, because if you ignore the outer one, which we're going to start in the center and work our way out, it is very common for the first part of what we solve to actually be something that you might well do, because it's a very common one to work with. Finding the magnetic field around a current-carrying wire. In fact, we'll find that you may have seen that equation before. Then it will become a very difficult equation as we start getting into the outer coaxial sheath that goes around it. All right, so here's what we're going to do. We're going to split this up into parts. We're going to find the magnetic field as a function of r for the region 0 is less than little r is less than big R. So we're going to be working at first in here where the current is actually going through here. I forgot to mention it. We're going to say that we have a current coming out of the board here of I out of the board. And we also have a current going into the board all around this whole thing that the total will come up to also I. So we have I coming out and I going in. And I'm also going to say that we have a uniform distribution of that current. In other words, the current is evenly distributed over all the area, the cross-sectional area of our wire. All right, so here's what we're going to do. We're going to start off, we're looking inside the wire, the innermost wire, and we know that the current is coming out and it's nice and uniform. I should be drawing dots evenly spaced, but you get the idea. We are going to some distance from the dead center R. It varies from 0 to big R, where big R is the outer edge of this. All right. So I'm going to draw my Amperian loop. Now, once again, Gauss's law has a bubble encasing a volume. Ampere's law is a ring or a loop that we put around, and it encloses an area. So we're not finding the magnetic flux here, we're actually finding out how much of the magnetic field is running along this loop. We can apply Ampere's law on this section, and we get that the closed integral of the magnetic field along the outside edge of our ring, we're going to integrate around our ring, is going to be equal to mu naught times our enclosed charge. Just like Gauss's law, since we're starting in the difficult part, which is in the middle here, we're going to have to end up with something called a current density. We know that we have a total current of I throughout this entire cross-section of the wire. So I can find the current density, which is usually a J, sometimes with a vector sign, sometimes just a J. I usually like to see the current as a vector because it does have a direction. In this case, it is coming out of the board. So I'm going to call it J with a vector sign. It is going to be equal to our total current, its vector, divided by the cross-sectional area that that current is applied over. In this case, we have our total current of I. That's the current that I gave you, that we have I coming out of the board, divided by the cross-sectional area, total cross-sectional area that it's distributed over, which is pi capital R squared. If I want to find the current that is enclosed, then I'm finding this region here. So this is my current density, which is uniform across the entire cross-section of the wire. I can find I enclosed by taking my current density and multiplying it by the area enclosed. This is exactly like what we did with Gauss's law. We would take the charge density per charge per unit volume and multiply it by the enclosed volume so that we could find the total charge in our bubble. By the same token, we have taken the total current, divided it evenly, because it's a uniform distribution, over an area, And now when we multiply by the area enclosed, just the red area here, it will tell us how much current we have inside. My I enclosed for this inner one is going to be equal to, well, J, the current density, which is I, the total current in the wire, times pi r squared, where r is capital R. And we're going to multiply it by the area enclosed, which is pi little r squared. The pi's cancel out, and we're going to find that the current enclosed is basically an area ratio of the area that we have, r little r squared, divided by the area of the total thing, big R squared. In short, we get the following. Closed integral of B dot dl equals mu naught times our enclosed charge, which is going to be I times little r squared over big R squared. That's my current enclosed. It is my current density times the enclosed area, which will give me the enclosed current. All right, the idea behind this is we're going to end up just like with Gauss's law, where we have a uniform magnetic field at this distance r. So since it's a constant magnetic field, at least for that distance r, it can be pulled out of the integral, and we end up with B integral of dl is equal to mu times the current, total current in the wire, times r squared over big R squared. I'm going to be adding up all the infinitely small little dl's here. We're looking at an infinitely small little bit of the length around here. If I add up all of those, I end up with, like with Gauss's law, we end up with the total area. In this case, we will find the total length around our Amperian ring, which, well, what's the distance around a circular ring like that? It's the circumference, which means our magnetic field technically dotted with the circumference, which is going to be 2 pi little r, because we're looking at the circumference at our Amperian ring at a radius of little r, is equal to mu naught I little r squared over big R squared. We can now solve for our magnetic field, although real quick, the dot product. Since we have a current coming out of the board, we use right-hand rule. We point the thumb of our right hand in the direction of the current, and we know that the magnetic field at this distance r, and pretty much all of them, for instance, is going to go this way. It is going to go counterclockwise. Let's go ahead and say that we integrate around the length the same way, counterclockwise. So at every given point, dl points exactly the same way as B does. And so the angle between them is always 0. The dot product simplifies down to cosine of the angle between them. Cosine of 0 is 1, and we get the following, that B times 2 pi little r equals mu naught I little r squared over big R squared. I want to solve for B, so B as a function of r is going to be equal to mu naught times I, let's see, one of the r's is going to cancel out, times r divided by 2 pi big R squared. In short, this r cancels out one of those r's. Mu naught, the current, 2 and pi, and big R for that matter, are all constants. Little r is the only thing that changes. So as we move outward in this wire, our magnetic field will actually grow at the same rate as, well, we go out. It's directly proportional to r. In short, as we go out, if I were to graph my magnetic field, in fact, I'll go ahead and set up a graph and we'll come back to it as we fill in more. So in this case, if we start, if we're graphing the magnetic field as a function of r, if we start here at 0 and we go all the way up to r, we know that it increases linearly. Great. All right. Now let's take a look at the next part. This one's a little bit trickier than the next part that we have. I have the wire here with the current coming out of the board, and we've got the next wire that starts in here. I'm not going to draw this part in, but we are looking for the region between R and 2R. We found the magnetic field in here. It increases as the little r increases, so it increases linearly. All right, here's what we're going to do. We're now going to find for our next region, we want to find the magnetic field as a function of r for the region of big R is less than or equal to little r is less than or equal to 2 big R. We're going to find in the region between the inner wire and the inside edge of the outer wire. So we're going to have an Amperian loop here. I'm going to go a little bit faster on this one. Again, the magnetic field from this one is going to go counterclockwise. We're also going to integrate in that direction. I'm going to set this up real quick. We have the closed integral of B dot dl equals mu naught times our current enclosed. And here's the beautiful part. Now we're not in an area that as we go farther out, we get more current. In this section, our current enclosed is simply I. Great. All right. Our magnetic field will also be constant with respect to, well, as long as we have a constant R. And so we end up with the following, that we end up with B times the integral of dl. Once again, it goes this way, counterclockwise, the magnetic field, and we'll integrate dl that way, so our dot product will simplify down to just 1. And that'll be equal to mu naught. I'm just going to write I, because our enclosed current is the total current I coming out of the board. That's the only amount inside our Amperian loop inside our ring. This, since the magnetic field is constant, we end up with this evaluating to, once again, the circumference of our Amperian loop, and we end up with the following. The magnetic field outside of a wire carrying a current is equal to mu naught times the current in the wire divided by 2 pi r. Hopefully this looks familiar because one of the default equations on the APC exam is the magnetic field from a current carrying wire. It's mu naught times the current in the wire divided by 2 pi r. This is Amperes law actually deriving that. So here's where that equation comes from. All right, we have something that drops off as 1 over r. It's a linear drop off. So let's see what happens in the next region. Here's where life is suddenly going to get much more complicated. So we showed you just now the first two parts, which are pretty common and relatively easy. We're now about to work on the next part, which is actually a lot less pleasant. You're going to find that it's the exact same stuff that we've been doing. It's just going to have a little bit more numbers, especially with what I've got set up in here. So it'll be a little bit more of a pain. All right. We have a total current coming out of the board of I. We have a total current going into the board of I, but we're not going to have all of that current because our Amperian loop this time is going to be out here. We're going to find the magnetic field as a function of R for the region of, let's see, 2R is less than or equal to little r is less than or equal to 3R. Great. Check on the camera real quick. Okay, so I had to check a couple things, but we're back. And we're going to talk about this, although I will bring up that I forgot to actually fill in this. It's going to be difficult for us to fill in this whole thing as a function of R for the entire coaxial cable. So I will bring up that this we found increases linearly as R, and the other one is a 1 over R dependence, and so this is going to trail off in a downward 1 over R relationship. We could go through and we could try and incorporate the others, although it's going to start to get very complex, so I'm actually going to skip over that. Let's see what happens with the outer sheath. So this is kind of the setup of the normal basic problem, and as I mentioned before things got switched out, here we go. We're going to look at the region from 2R to 3R, so we're going to look inside this total sheath. Now, the way we're going to deal with this is the same thing that we did with Gauss's law, where we're going to start incorporating the idea of your total current enclosed. And your current does have a direction along with it. So we've got I coming out of the board, and once we get to the outside edge, we will have I going into the board, and they're going to work against each other. But while we are only part way out, we have total I coming out of the board, and only part of I going into the board. So our trickiest part on this is going to be to find the current enclosed. So here we go. We know that for our Amperian loop, we're going to apply B dot dl equals mu naught times I enclosed. The hardest part about this is going to be dealing with that I enclosed. All right. In fact, the magnetic field is going to be constant, and dl is going to integrate to this. So I'm going to go ahead and fill this in. We've got b times 2 pi r, for r being the radius of our Amperian ring, our Amperian loop. And I've got mu naught times I enclosed. We need to find I enclosed and see how much, if any, it is a function of r, because it very well might be. And this is going to be why it's going to be kind of complex to try and graph that. So we're going to take a look at what this is going to be. All right. Here's the thing. We know that we've got the current I. We could call it negative I, in fact, because it's going into the board. Keep track of the direction, but we'll add that here in just a minute. For now, to avoid dealing with the extra negative, I'm just going to see what happens as I spread this out. Now, what I need to find my current density for this second wire, this ringed wire, if you will, it's going to be our total current, which we could call negative I, divided by our total area on the ring itself. Now I'm going to, as I said, drop the negative for a little bit, but we know that later on when we deal with our current density in the second area, that will actually be a negative current because it's going to go into the board, and we're going to say coming out of the board is defined to be positive. In this case, we know that we have a total current of I divided by, here's where things are going to get tricky. We need the area of this ring, the total area, which is going to be, we could take, let me draw this out. To find the area of a ring, we could take the area of a giant circle and then subtract off the area of the missing part of that. So it's one circle minus the other circle, and that will leave the area around this ring. So what we end up with is the following. The area of the outer ring, which is pi quantity 3r squared, minus the area of the inner ring, which is pi quantity 2r squared. I should actually use brackets just to make things proper. But this is the outer area, the green, its entire area, minus the inner area, this red area, and what will be left will be just the area of the outer ring. So, like I said, this is going to get a little unpleasant because our current density in the second wire, the ring wire, is going to be equal to negative, technically I, divided by the quantity of, I'm going to expand this just a little bit to clean it up some. We're going to have pi times, this is going to be 9r squared, for 3r quantity squared, minus 2r squared, which would be 4r squared. I can clean this up a little bit more, and we find that the current density is going to be equal to I divided by 9 minus 4. That's 5 pi big R squared. Looks a lot nicer when we actually put that in. I will say this is one of the reasons why I went ahead and did R, 2R, and 3R, so I could clean this up into a nicer form. All right, let's find this is the current density. So this is us actually distributing I evenly along this area of the ring. If we want to find I enclosed for the second wire, that's going to be equal to J2, the current density, times the area enclosed of the second wire, which once again, take a look at this, the green and red that I drew before. This time, what we're going to end up with is J2, which we said was I over 5 pi big R squared times the area enclosed, which is going to be pi little r squared minus pi 2r quantity squared. The inner shell here, where it starts bringing current in, is at 2r, and we're looking for the amount that we have enclosed, which is going to go out to our Amperian ring from the 2r. So I have my outer area be that of the Amperian ring, and the inner area to be the inside edge where the current starts coming in. All right. This is the current enclosed in the second wire. for us to find our total enclosed current, it's going to be equal to the current from wire 1, which is just I, minus, and here's where we could incorporate the minus here, but it's going to be minus I enclosed 2, however much is enclosed in 2. I'm going to clean this up a little bit. The pi's actually cancel out, and we get the following. Our current enclosed for this region, again, not terribly pleasant, is our total I positive coming out of the board minus our current enclosed in wire 2, which we said was right here. It is I times the quantity of little r squared minus 4 big R squared. That's this part here, little r squared minus 4 big R squared, divided by the quantity of 5 big R squared. Let's check something real quick. When we get to the outside edge, when little r reaches 3R, we know that our total enclosed current, we have positive I going here and negative I going there. Let's check something. Now that we've come up with the idea of I enclosed, let's check I enclosed at R is equal to 3 capital R. And just make certain that we come up with what we should, which is 0, because we have just as much coming out as we do going in. So if I were to check that real quick, I'm going to do it in a different color. We've got I minus I times little r becomes 3r, quantity squared, minus 4r squared over 5r squared. This is going to be the same thing as I minus I times the quantity of 3r squared is going to be 9r squared minus 4r squared over 5r squared. And hey, look at that. The r squareds cancel out. And we have 9 minus 4, which is 5, divided by 5. This whole thing becomes 1, and we have the total current minus the total current, giving us a total enclosed current of 0 when we get for little r is equal to 3 big R, and that matches with what we expect. It's a good thing whenever you get the chance to, if you've got the time, go through and double check your boundary conditions, what happens at the extremes. I know when I get to the outside edge of that coaxial cable, since I have just as much current coming out as I do going in, I should have a total enclosed current of 0, and we find that we actually get that. Finishing this up. Now that we've got a workable value for our current enclosed for our final region, we get the following. We have the rest of this done, so I'm going to scroll down here. We know that B times 2 pi little r is going to be equal to, so this is B dot dl, the integral of B dot dl. B was a constant, we pulled it out, and dl evaluated to 2 pi r, the circumference of our Amperian ring, equals mu naught times our current enclosed, which is going to be I minus I times, I guess I need brackets, sorry, times little r squared minus 4 big R squared over 5 big R squared. There we go. That's our current enclosed. We end up with the following, that our magnetic field inside that region is going to be mu naught times, well, all of this mess, I minus I times little r squared minus 4 big R squared over 5 big R squared, all over 2 pi r. Now, this is why I'm not actually going to do much else with this right now. You can see that we have an r squared up here, but we also have a divided by r down here. But because we have some unpleasant terms with some constants, I'd have to do a little bit more math to see exactly what the graph looks like. But the important thing is this. This is the actual equation. If we check that r is equal to 2r, for instance, let's try the inner edge. So if little r is right at the inside edge, 2r, we could put in 2r in here. That would become 4r squared minus 4r squared, that's 0. I times 0 is 0, and we would just have what we found in that region before, that it would be mu naught times I divided by 2 pi r. If we check it at little r goes to 3r, then this becomes 9r squared, and as we saw before, this becomes 1, and we have I minus I. We end up with 0 net current enclosed, and we will therefore end up with a magnetic field of 0. And that actually gets us set up for our very final one. If we're outside the thing altogether, if I do my Amperian loop out here, I'm not even dotting it, but we know that our I enclosed is actually going to be equal to 0 amps, 0 total, because we have just as much coming out as we have going in. So we will actually find that the magnetic field outside of this wire is actually equal to 0 Tesla, because we have no net enclosed current. I'm going to mention this, but we're not actually going to develop it much more, at least in this video or anything else that I know of right offhand, but if we get some extra time. This is actually the same mechanism that GFCI outlets work on. So the electrical sockets that you hit reset and test on, they're designed to save lives, and they actually rely on the fact that as long as the same amount of current is coming out as going in, then you end up with no net magnetic field. If you have a slight difference in how much current is coming out versus how much goes in, you will end up with a net magnetic field, and that will actually trip it and kill the circuit because charges are going somewhere they're not supposed to. We want all of the charges that go into the house to come back out of the house. And if you drop, say, an electrical device in a bathtub or something like that, charges will leave through the water and not come back out the far end of the circuit, giving you a difference in your currents, which means your enclosed current will not be equal to 0, and your net magnetic field will not be equal to 0 either. It's actually a really good way to determine a small change in current, because it can detect a little bit of difference in current because your magnetic field goes from 0 to something not 0. All right, we'll go ahead and stop there. That's Amperes Law.